put I2 max, it means that I'm going to find out all the values at resonance. So I2 max will be equal to minus V1 Z21. Z21 is j omega m. So minus V1 into j omega naught MC divided by Z1122 Ri dash R naught dash minus Z12 square. So plus omega naught square MC square. See, if you are not understanding where did we get this equation, we are substituting the expression for all the terms which are highlighted in the above slide in the equation for A2. See, all these values are happening at resonance. You know, at resonance, the current is maximum. So I replace I2 by this. I2 becomes I2 max and substitute all the values at resonance. So if you simplify, you get minus j V1 omega naught MC by R naught dash Ra dash plus omega naught square MC. But we know that we have derived yesterday this relation. MC is equal to root of R naught into Ra dash. We have derived this equation for maximum power transfer. So during the resonant frequency, when M will be equal to MC, this condition will be holding good. So I try to replace this term with R naught into Ri dash. So you note omega naught square MC square is also equal to R naught dash into Ri dash as per the maximum power transfer conditions. So denominator you see, numerator is going to be same minus j V1. Also omega naught MC is root of R naught dash into Ra dash divided by R naught dash plus Ra dash already there. This one is also equal to R naught dash into Ra dash. So when you simplify, denominator is 2 R naught dash into Ra dash. Numerator you have square root of R naught dash into Ra dash. So one square root I can cancel. So it becomes minus j V1 by 2 into square root of R naught dash into Ra dash. When you take modulus of the maximum current, modulus of minus j is going to be 1. So it is going to be V1 by 2 into root of R naught dash into Ra dash. So this is the value of current at resonance, substituting all the parameters. And if you draw the graph for the current versus frequency, this is how it will look like. I2 is going to be the secondary current, right? So when you are going to operate the amplifier at less than the critical coupling, when K is less than Kc, which we usually do, always we will not let the coupling coefficient reach the critical value of coupling. When K is less than Kc, this is the response you get, which is response of a normal tuned amplifier. At exactly the critical coupling, when K is equal to Kc, you know the current is going to be maximum. And when you have conditions where the critical coupling coefficient is going to be larger than the Kc, so the second case is K is equal to Kc, and this last case is K greater than Kc. So when you have a greater coupling, critical coupling coefficient, then it is observed that the secondary current has two peaks. This was found from experiment. So secondary current is going to have two peaks. So we are going to find out what is the frequency at which the current is going to have two peaks. So for coupling greater than the coupling critical coupling, the power transfer is maximum at two frequencies. See, this is not the frequency response, this is only the secondary current characteristics. So don't confuse this graph with the frequency response graph. This is only going to be the secondary current characteristics. So when you operate the device at a coupling coefficient more than the critical coupling, it is experimentally found that the power transfer is happening at maximum power transfer is happening at two frequencies, which was actually happening at only one particular frequency when the K value is less than Kc. So when you keep on increasing the coefficient of coupling beyond the critical coupling factor, it is found that the power transfer appears at two frequencies where the transfer is going to be